Thank you, Abhishek, and thanks to all the organizers for the invitation to this very interesting meeting. And I flashed this at the beginning just to show you that we have an active center in Korea, and we currently count 5 members from India, so it's nice to be in our own country, a significant part of members right now. So I will talk about work which was, is, and I guess also will be done in together with, including also discussions and research together with these people, Altschuler, Campbell, Czerny, Danieli, Fistul, Kati, and Tudja Dangal. And this is in alphabetic order, which by no means represents contributions of the individuals. Mainly, I will talk about the dynamics of classical extended systems in the proximity to integrable limits and to properties of non-integrable networks and the corresponding impacts. So I will study systems which I assume are ergodic. Now there might be different views on what that means, and for this talk here, if you want, you can blame me for that, but this is our working platform. We assume that we have a conservative Hamiltonian system with many degrees of freedom, where the dynamics is subject to certain constraints, at least say to preserving the energy, and that cuts out a certain available phase space in the full phase space of my system. And I'm now assuming that there is a set of points of measure 1 through which trajectories run, which are called by us ergodic, which means loosely that each of these trajectories visits any point on the available phase space in some due time, which in particular also assumes that the infinite time averages of any observable you may pick should then be equal to the corresponding phase space averages of the same observable, and an observable is nothing but a function on the phase space itself. This doesn't exclude the possibility to have a set of points of measure 0, which can belong to non-ergodic trajectories, such as, for instance, periodic orbits, which we heard already about. So that's the setup, and I'm assuming that we have an ergodic system, and then we want to see how this ergodicity is in some way lost. What are the different ways you can suddenly lose ergodicity in such a many-body classical system? Well, one possibility is that they don't have that many bodies, so to say, not this, you have a limited number of degrees of freedom, and then if you tune your system through parameters to the proximity of an integrable limit, then you can enter the Kolmogorov, Arnold, Moser or CAM regime, where most of the dynamics will happen on invariant CAM tori. And I will not, I will say a few more words about that, but this is not the point of interest of this talk. Another possibility is that you can tune your, fine-tune, so to say, your initial conditions to be in the proximity of this mentioned non-ergodic set of points of measure 0. And I'm arguing that one way of viewing the famous Fermi-Pastor-Ulam paradox and problem precisely belonging to this item here. Another possibility to lose ergodicity is to consider systems which have additional constraints which force you into some strange non-Gibbs dynamics, which essentially looks like a condensation phenomenon. An interesting field also, and I will touch it very briefly, but not the main target of this talk. The main target of this talk is whatever is left if you throw out all the others, which is you have a macroscopic or very large number of degrees of freedom, and you simply want, so you're out of the CAM regime, and you don't have additional constraints which force some condensation, and you are not fine-tuning your initial conditions. And then you want to go close to an integrable limit, and then we want to understand how the ergodization dynamics is slowing down. But just to mention again on the other, briefly on the other ways to lose ergodicity. So this is again just remind you about the CAM theorem. You have an integrable Hamiltonian, which depends only on the actions, and then you add but a finite number of them, and then you add a weak non-integrable perturbation, and the statement of Kolmogorov, Arnold, and Moser was that for very weak perturbations, most of the tori of the integrable dynamics will be somehow deformed, but survive and fill a finite part of the phase space. So, which means that in some action space, what you will find that the original actions will, of course, start now to weakly depend on time, but they will still oscillate around some mean value, which is far from some Gibbs average over the whole available phase space of the now non-integrable system. And it's believed that the thresholds up to which this CAM theorem holds will deteriorate probably even exponentially fast with an increasing number of degrees of freedom. So therefore, this is apparently not an issue for macroscopic systems. Fermi-Pastor-Ulam problem is, to remind you, a problem essentially of fine-tuning. You take a non-integrable system, a chain of oscillators, and you excite a normal mode, which is a solution of the integrable linear part of this system, and then you let the system go, and you expect, or Fermi and Pastor and Ulam were expecting that the energy of this mode will be shared in due time with all the other degrees of freedom in the system. But this doesn't happen, at least over very long times, and what you find is that only a few modes share the energy of the initially excited one. So you see some kind of mode localization, which is clearly not a very ergodic behavior. Essentially, if you wait long enough, you will see a gradual destruction and route to equipartition in such systems. So the problem is actually not so much about rigorous breaking of ergodicity, but it's a problem of having several timescales which can be severely different from each other and sensitively depend on some parameter tunings. And we contributed to this field with a statement with a proof of the existence of exact time periodic orbits in these very non-integrable systems, which are periodic in time but localized in normal mode space. And therefore, we concluded that one way of interpreting the observed Fermi-Pastor-Ulam paradox is that it is nothing but a perturbation of an exact periodic orbit. So you choose an initial condition which is in some proximity to these non-ergodic solutions, which in principle of measure zero. And then for long times, the trajectory will stick to this neighborhood. And that is what you will observe. And then the second time scale is the time scale of final escape from this narrow region. And then there is finally this condensation effect, which I mentioned, which can happen, for instance, if you take a Gross-Pitayevsky lattice, a nonlinear Schrödinger lattice, or for instance, also a Bose-Hubbard lattice, if you want to take the bosonic quantum version, where you have not only the energy being conserved, but also the number of particles. And that leads to, in the microcanonical system, to a region, a finite region in the density parameter, control parameter space, which is not describable anymore by a Gibbs distribution. And if you launch your dynamics of your system, of your microcanonical system in that region, what you will find is a kind of a segregation of the field into two components. One, which is kind of like a condensate, and if you wish, is a manifestation of a non-ergodicity because it doesn't really participate anymore in the further dynamics, which happens in order to allow the rest, the second part of the field, the second component, to happily stay ergodic at some infinite temperature. Right, but this is again what how you can also run into non-ergodic features. But here I basically just want to study a system with many degrees of freedom in proximity to an integrable limit. I assume that the system has a countable action and angle set. And we want to identify different classes of non-integrable perturbations, perhaps quantify the process of thermalization or ergodization of our system, and perhaps see novel dynamical regimes. So Another reason why we ran into this project, into this set of projects, was this interesting paper by Pino, Joffe, and Altschuler from 2016, where they studied the quantum chain of Josephson junctions, which enjoys translational invariance, and claimed or produced some results that this system has a many-body localized phase. But then, of course, it has a transition into a metallic phase, and the metallic phase was predicted also to have a non-ergodic part of it. And this non-ergodic metallic phase was then predicted to survive in the classical limit of this Hamiltonian system. And then they provided with some numerical evidence that indeed the classical system shows non-ergodic behavior. So that was certainly of interest for us to study in more detail. And one upshot of the results is that it's a matter of time and system size scales. And according to our understanding, the classical version is fully ergodic. But it has some interesting peculiarities in the way this ergodicity is achieved. So if we want to study whether a system is ergodic, we could simply test whether infinite time averages of observables equal ensemble averages. But since we don't have infinite time at disposal, we can compute at least finite time averages of observables, but these will depend on the initial conditions. Then we can select many different initial conditions. We can, so to say, scan our whole available phase space, and then we'll obtain a distribution of finite time averages. And then we can study how these distributions and the parameters which characterize these finite time average distributions will depend on the averaging time itself. In particular, we expect that, of course, if the system is ergodic, then any finite time average distribution of some observables which has some finite width should collapse into a delta function in the limit of infinite averaging times, such that the second line will then hold. So for that, we have to choose observables. And that's in general quite a tricky point. I think also in many talks here, we have been witnessing that. Now, since we want to be in the proximity of an integrable limit, it seems to us that the natural choice of the observables are simply the actions which become the conserved quantities at the integrable limit, or maybe some simple monotonous functions of them. But in general, if you are far from an integrable limit, then the choice, choosing the right observables is quite an important and interesting, non-trivial thing which sometimes relies on your intuition. So we choose here the actions, and then we simply compute finite time averages of these actions and look at the distributions and then characterize the width of these distributions. Just a few lines of formula here. So if f is my is any of these actions is my observable, here is the finite time average. Capital T is the averaging time. Rho is then the distribution of these finite time averages, which parametrically depends on the averaging time t. The first moment of this distribution is t independent because of the simple fact that time and integration and integration over phase space commute for the first moment. But all the higher moments will, of course, in general depend on the averaging time. And you will later see various quantities. It can be either simply the second moment, the naked second moment, which I will plot, or I will calculate the standard deviation sigma and then plot sigma squared, or I will plot sigma squared divided by the standard deviation divided by, I'm sorry, the variance divided by the square of the first moment in case this first moment is non-zero. And then I will plot the little q. So you sometimes will see potpourri here of different things on the y-axis, but they all mean the same. They're all related to the second moment of the distribution function. And just by walking by, I want to mention that this variance of the finite time average distribution is given also by the time average, the finite time average of the autocorrelation function of the same observable. So in principle, you could also calculate correlation functions, time-dependent correlation functions. and then integrate them over a finite time, divide by this time, and again obtain the variance sigma squared. Right, so if we have our set of j and theta of countable action angles, then the Hamiltonian is, say, given by an integrable part h naught and then a non-integrable perturbation. And what I'm now arguing for is that this perturbation h1 spans a certain interaction network on the space of the actions, or on the lattice, if you wish, where each lattice point corresponds to one action jk. And that network range will control the many-body dynamics and also the way the system will ergodize or thermalize. So what you see in these equations here, this is the equations of motion for one of these actions, jk. And then on the right-hand side, if you write it out for most of the models, at least which we were looking at, the right-hand side becomes a sum over many terms, and each term is something I call here an L-tuple. So each term in the cases I will discuss will be a product of, or a function, let's say, of L other actions. And then there are R such terms on the right-hand side. So L is typically finite. In the cases we looked at, this can be 2, 3, or 4, which corresponds to some degree of nonlinearity, two-body interactions in quantum language, or three-body interactions, and so on. But R can be very different. R can be either stay finite and volume independent if you increase your system size, and that means that you have a short-range non-integrable network. The other opposite case, R can actually increase with the volume in a certain way, which means that you have more and more terms here on the right-hand side, which you have to sum up as you increase the size of your system, and that means that you have a long-range non-integrable network. Right, and then also, which I will not dwell on this in detail, but you can try to work out then some notion of resonances. You take one of these terms here on the right-hand side, so one of these L tuples, and then you can try to work out in a very naive way a certain condition for a nonlinear resonance, which essentially wraps up to compute some frequency difference of all the actions involved in on the left-hand side and in this one term on the right-hand side. And just remind you that the frequencies are just given by the derivatives of the angles. And so this is this delta omega, and then there's some smooth function of the actions themselves. And then there's, of course, the perturbation strength of the non-integrable part, epsilon. And then you have to satisfy some inequality of this type in order to convince yourself that you have a nonlinear resonance. Right, and for those of you who want now to do other things, just a quick and incomplete summary before I continue. So basically what we'll find, if we look at the variance of the finite time average distributions as a function of time, is a behavior which in this caricature here looks like that. The variance may stay for quite some time, quite some long time. Longer and longer times, the closer you come to the integrable limit constant, which means that your actions essentially don't change over long times, and therefore the distribution function doesn't change its profile and its width. But then once you reach this ergodization time, as we call it, which is a function of the proximity distance to the integrable limit, the distribution function will start to shrink, and ultimately, we think at least, it will reach this delta function limit. And right, and this decay here will be given by 1 over the averaging time to the power alpha, where alpha is 1 for a long-range network, but 1/2 for a short-range network. 1/2 signals fusion. There's much more to say, but that's maybe a short wrap-up of. I will now go on into more detail. So, and let's just pick the very Hamiltonian system, which I mentioned already, this system of coupled Josephson junction chains in the classical version, of course. Well, you can give these terms here names which come from the Josephson physics, where this is the Josephson energy, EJ, and these Qs here will be the phases of the superconducting water parameter on each superconducting island, and this here will be the charging energy on each superconducting island. But you can also simply say that you have rotors, where P is the angular momentum of each of these rotors, and the Qs are the angles of these rotors, and you have a nearest neighbor coupling. The number of sites sometimes is written as capital N, and then there is an energy, a total energy H, which is conserved, and then therefore there's an energy density, little h, which is capital H divided by. So let's see, this model has, as many other models apparently, has both long and short range network limits incorporated depending on how you change the parameters. Let's first consider the case where the energy density H divided by the Josephson energy is much less than 1 and say tends to 0. So that's your Hamiltonian, and then it takes you a second to realize that in that limit, in leading order, you just leave the quadratic term from the cosine potential here. You end up with a harmonic chain. That's, of course, an integrable system with the actions corresponding to the energies of normal modes, and the normal modes are extended objects, if you wish, in real space because of the translational invariance of this problem. And then the first non-integrable correction comes from the quartic term expansion of this cosine written down here. And if you add both together, you basically end up with something which some of you would call a Fermi-Pastor-Ulam, beta Fermi-Pastor-Ulam model. So that non-integral perturbation imposes a long-range network. Why? Because the normal modes are extended over the whole system, and these quartic terms, though it's a sum of local terms, they couple essentially all modes to each other. In a very small version, you can maybe, if you look carefully, see the equations of motion for the actions J, and you see here a triple sum over different indices, and that already indicates to you that you have here a number of terms which grows in some way as you increase the system size. In fact, the number grows as n squared. There are three sums here, but one sum goes away because there's an additional vertex here. It's a selection rule because momentum conservation, if you wish, because you have a translation invariant system. So, but you are still left with n squared terms here on the right-hand side. So R is n squared, and we have three tuples, or we have three different new actions on the right-hand side which couple to a given action. So that's a long-range network. And then if you compute the finite time average distributions for different actions, and then here I plot Q, it's still the same sigma squared, or the second moment related to the second moment of the finite time average distribution function. You see what I told you already. It stays constant up to some time. This is log here, and then it starts to decay, and this decay is postponed as you approach the integrable limit, and the decay essentially is 1 over t. There's an interesting thing though. Here you see some little features, some little shoulders here, and these little shoulders indicate that a certain part of your set of degrees of freedom resists thermalization, at least on these timescales. And that is more pronounced seen if you dig a bit more into the numerics. Here in this picture, indeed, you find that the finite time average distribution stays at a constant width at shortened times. Then it starts to shrink, and then it kind of stops shrinking at some finite value of the width, only to resume then the decay at some later time. The reason for that is that that a certain part of your a certain number of your actions in your system resists to be resonant. So basically, you analyze, you look whether a reference action belongs to a group of actions which are interacting resonantly or not. And then you find that in principle, for each L tuple, the probability of an action to be in resonance with the other actions in that L tuple becomes very small as you come close to the integrable limit. But there are many of these L tuples, and therefore, at the end of the day, what you can work out is that the number of resonant actions is almost, the fraction of the resonant actions is almost 1. So the number is almost n, and the number of non-resonant actions is very small, but still non-zero. And very small means actually exponentially small. It becomes exponentially small with increasing system size at a fixed distance from the integrable limit. Nevertheless, this number is finite, and exactly at this ratio, at this fraction value of the non-resonant actions, you will find that the distribution function width stops decreasing for some time. So basically, what you have here is you start your initial, you start your system, and you have, say, a big fraction of actions which are already resonantly interacting with each other, but there's a group of actions which is not resonant. So what happens is that first the resonant actions start to thermalize. The non-resonant actions do not participate in that. So you have some kind of partial non-ergodicity in this subpart of the actions. But since all actions are coupled to each other, finally the thermalized actions will drive the non-resonant ones, if you wish, and finally the whole system reaches a nice ergodicity properties some later times. And just bypassing that, I don't show you the details. This onset of the ergodization process, which happens at some time TE, scales with the square of the Lyapunov time, and the Lyapunov time is the inverse of the largest Lyapunov exponent in this. It becomes very different if you go to the opposite case of a short-range network. In the same model, you simply tune this ratio H energy density over Josephson energy into the opposite limit. You make it very big, so the inverse will be small. In that limit, you can do this simply by tuning EJ to 0, right? In that limit, you trivially obtain another integrable system, namely of uncoupled or free rotors. And then the non-integrable perturbation will be simply this whole Josephson energy term here. And that clearly imposes a short-range network on the set of your actions at the integrable limit. And now what you find here, if you again do the analysis for the resonances, is if you come close to the integrable limit, a certain pair or triplet of rotors or of actions might become resonant, but this probability will be very small simply because epsilon is very small, or because this number is very big. But since each action only has two tuples with whom it can interact, then it means that you have a very sparse distribution of resonances in your system, and the average distance between resonances becomes larger and larger as you tune your system closer to the integrable limit. So what you then find is a bit different from the long-range network, namely, again, in principle, if you just look naively, you see that the distribution function of finite time averages first stays constant and then starts to decay. So here is my, so to say, ergodization time, beyond which I start to see a collapse of my distribution. But if you look more carefully, what you find is that this decay now is not 1 over time, not 1 over averaging time, but 1 over square root of averaging time. If you have a finite system, then for your finite system, you will follow this 1 over square root law up to some point in time, from where on you depart and you recover the 1 over t decay. But this 1 over t decay is postponed to infinite times if you increase the system size to infinity. So for an infinite system, what you will find is once you reach your ergodization time is a 1 over square root of time decay of the distribution function, which by the way means also that your correlation functions in time decay as 1 over square root of time. And essentially this is a diffusion process, and so what we think, this is more of an interpretation than a rigorous statement. You have these rare resonances in your system which have a typical distance which, well, this is not correct, of course, should be 1 over epsilon squared here. So the distance for small epsilon becomes very big between, on average, between these resonances. So in these resonances, you have chaotic dynamics, and all the rest is essentially evolving regularly. Now, what's happening is that these resonances drive nearby rotors and slowly tune their momenta. And finally, with some probability, some of them will enter a new resonance condition. And so essentially what you see is a diffusion of resonances. And this diffusion of resonance process manifests itself in this 1 over square root decay of the convergence of the width of your distribution function, finite time averages. And so essentially now here the task then is to identify this diffusion coefficient and to understand how it depends on the proximity to the integrable limit. So I will skip many details. We did many more tests to verify that this picture has some basis, did some scaling. Let me not talk about all these numerical details, just come to the point here. So here's this diffusion coefficient, which we extract from our numerical analysis versus 1 over the Josephson energy. So I remind you again, so this is for energy density 1. So if EJ goes to 0, we reach the integrable limit. So we have to march to the right to reach the integrable limit. And you see we vary here this Josephson energy over a very relatively small interval. So 1 over J varies from 1 to 4. And at the same time, the diffusion coefficient, which we measure from our data, varies over a bit more than 3 orders of magnitude. Now the question is, what is it? Yeah, is it exponential, or is it a power law, or what is it? So we had lots of debates. They are unsettled. This is the plot of one of the outcomes of these debates. So that could suggest to you that you see some kind of exponential zeroing of this diffusion coefficient with increasing 1 over EJ. But I'm not so sure about it, and I think there's lots of room for further discussions with those who do simulations and calculations of similar systems and approach such quantities perhaps from a different perspective. Right. You can also, or we could also convince ourselves that yes, if we think that these diffusions which I was if these resonances I was talking about are the ones which drive the diffusion process, then you can just run your system and look in space-time where these resonances are located. So the black points here show you the positions of these resonances. This is space, a piece of the space. This is a piece of time. And then you indeed see some kind of slow migration of these resonances, of these black spots here as time evolves. Finally, maybe I want to mention show one result which was me at least quite surprising. Namely, if that is all true, if the whole process of ergodization and thermalization relies on these resonances to be there, to be chaotic for long times in order to incoherently drive neighboring actions or rotors, then if we somehow hinder this process from taking place, we could somehow postpone the ergodization and thermalization of the system. And for that, we did the following. We chose a random process. We just kick the system randomly. So it's like a noise. It would be very strange that I can, with a noise, delay relaxation into equilibrium rather than, because usually I will expect the opposite. But what we do here is we do the following. We take at every T lambda, I remind you again, this is the Lyapunov time, which is the inverse of the largest Lyapunov exponent. We randomly choose one of the sites. And then we change the momentum on that side by plus or minus delta P. And we vary delta P. And then, of course, I'm almost done. And then, of course, we have to correct, to do some corrections in order to make sure that the total energy doesn't change and also the total momentum doesn't change. We do that. So essentially, we jump from our given trajectory in our phase space to another one, but still in the same available phase space. And then what you see here is the width of my finite time average distribution as a function of averaging time. In the absence of this random process, delta P is equal to 0, we see what we have seen already before. And then if delta P is, what we expect is that if delta P is of the order of EJ, and EJ is 0.7, then we start to destroy with a certain probability resonances. And in principle, at times of the order of 10 to the 3, we can conclude that we, on average, reach every site in this random process. So we should be able to reach any resonance by that time. And indeed, at these times, we see for delta P is 0.6, some little hump which develops here, which becomes even more pronounced as we increase delta P further, which means we postpone the collapse of our finite time average distribution by a random process, where we think what we really do is we destroy those resonances, at least on these time scales. And therefore, this diffusion process of resonances is halted at least up to a much longer time scale. Right, with that, I'm done. So there are some take-home messages. There are some publications. There's more work in progress. And these, again, are the people who were and are working together these issues. Thank you very much for your attention.
Questions?
So you showed this ergodization time that was going apparently exponentially, but then you said you're not sure. This is there was some plot, the ergodization time. Yeah, this is the right one. Yeah.
This is the diffusion constant. It's not the ergodization time. This is the diffusion constant.
Oh, that's the diffusion constant.
Which characterizes, we think, the diffusion of these resonances.
Okay, and what would be the behavior of the ergodization time when you approach this?
Okay, the ergodization time we measured before already, and what we find, let's say we take this case here, H is the energy density is 1, and here we vary the joules on energy, so it now becomes small when we go to the left. See that this ergodization time rapidly increases as well as we approach.
It's clear that it increases. Right. No, my question, how does it increase?
Well, this is a very good question. And at that time, when we did these calculations, we said it's power law. And then Wojciech came and said, cannot be, it must be exponential. And then if you start plotting the same data, you know, it's like, some people say, if give me this, whatever, 5 parameters and I can fit an elephant. And here I think, if it's the opposite, give me too few points and I can also fit almost any function you want. So it's very hard for me to tell this. I think this is open, completely open. There are many interesting things, I think, which still can study.
There are some analytical predictions for...
Well, I mean, ask Wojciech.
Okay.
I guess so. Am I saying the right thing? Or?
Well, does they apply?
I'm sorry, François. Sorry, François. Sorry. Yeah, ask François. Right. Sure.
Yeah, so we sort of prove a theorem, which I don't know anymore whether it exactly applies to this system. No, right? It's rotors, right? Rotors, right? So where the okay, we calculate something which is not exactly the diffusion constant, because of course mathematically you can never prove that the diffusion constant is smaller than infinity. But we have things that probably are quantifying the rate of thermalization, and they are exponentially small, not exponentially small, but faster decaying than any polynomial in epsilon.
Well, I think I can issue an expectation since I'm not a quantum physicist, so to say, compared to the majority of the people here. Well, I think it's quite probable that if you quantize the system for these short-range networks, that will have quite an impact on, so to say, these resonances. In some sense, in a semi-classical way of discussing the problem, I could expect that I will wash out these resonances and hinder thermalization even further, maybe up to a complete stop or not, that's a different story. But certainly this is an interesting regime or playground for MBL, and somehow I always was thinking that MBL happens usually in systems which are close to an integrable limit with a non-integrable short-range network imposed on that, but my personal.
So if there are no other questions, then let's thank Sergej.